In this video, we're going to be proving the derivative for the secant function, which is equal to secant of theta times tangent of theta through the definition of the derivative for any given function of x, which is equal to the limit, as our change in x represented by h goes to 0, of f of x plus h minus f of x divided by h. With this definition in mind, we can begin to prove the secant function's derivative through the definition of the derivative. So this is equal to the limit, as h goes to 0, of secant of theta plus h minus secant of theta divided by h. This can then be rewritten as the limit, as h goes to 0, of 1 over cosine of theta plus h minus 1 over cosine of theta divided by h. And the reason why I can do this is because the secant function is equal to 1 over the cosine function. Therefore, rewriting the secant of theta plus h as 1 over cosine of theta plus h and secant of theta as 1 over cosine of theta. And with this limit, what we can do is we can simplify the entire fraction and the numerator as a result. So this becomes the limit, as h goes to 0, of, if we combine the two terms, which is the expanded form of secant of theta plus h and secant of theta, we must give it a common denominator, which is the product of the two denominators of the two terms. So this becomes h times cosine of theta times cosine of theta times cosine of h minus sine of theta times sine of h. And in the numerator, we would have cosine of theta minus cosine of theta times cosine of h minus sine of theta times sine of h. You might be wondering where I got cosine of theta times cosine of h minus sine of theta and sine of h from. Well, I got this by expanding the cosine of theta plus h function, because we know the trigonometric identity of the cosine of the sum of two angles represented by theta and alpha will be equal to the cosine of theta function times cosine of alpha minus sine of theta times sine of alpha. So by multiplying cosine of theta plus h and cosine of theta, we will result in this term right here, and with the likewise reasoning, we will get the numerator as such. So with this, we can apply the negative symbol into our parentheses to get equal to the limit, as h goes to 0, of cosine of theta minus cosine of theta times cosine of h plus sine of theta times sine of h divided by h times cosine of theta times cosine of theta times cosine of h minus sine of theta times sine of h. And with this, we can further simplify the numerator by taking out a likewise term of cosine of theta present in this term and in cosine of theta times cosine of h. So we can rewrite this limit to be equal to the limit, as h goes to 0, of, in the numerator, cosine of theta times 1 minus cosine of h plus sine of theta times sine of h divided by our denominator of h times cosine of theta times cosine of theta times cosine of h minus sine of theta times sine of h. And what I can now do is break up this limit to be equal to the sum of two limits, which is equal to the limit, as h goes to 0, of cosine of theta times 1 minus cosine of h divided by our denominator of h times cosine of theta times cosine of theta times cosine of h minus sine of theta times sine of h, plus the limit, as h goes to 0, of sine of theta times sine of h divided by our denominator of cosine of theta times cosine of h minus sine of theta times sine of h. And what I can now do is, but before I move on to this, I must justify why I can do this. The reason why I can do this is because of a limit property, which is the limit, as x approaches to n, of the sum of two functions represented by f of x and g of x will be equal to the limit, as x goes to n, of our first function f of x plus the limit, as x goes to n, of our second function g of x. So if I expanded this limit as such to be equal to the product, or rather the sum of those two limits. So with these two limits, we can begin to process each limit piecewise. And we're going to first start off by evaluating this limit, which I underlined in green. And to evaluate this limit, we can break this limit to be equal to the product of two limits, which is equal to the limit, as h goes to 0, of 1 minus cosine of h divided by h times the limit, as h goes to 0, of cosine of theta times cosine of theta times cosine of h minus sine of theta times sine of h. And in the numerator, it will become cosine of theta. And the reason why I can do this is because of another limit property, which states that the limit, as x approaches to a value of n of the product of two functions represented by f of x and g of x will be equal to the limit as x approaches to n of our first function f of x times the limit as x goes to n of our second function g of x. So if I've broken up this limit as such, and to evaluate this limit, it'll be quite simple because we only need to analyze this limit, the limit as h goes to 0 of 1 minus cosine h divided by h. And we know from a limit property that the limit as x approaches to 0, our input of 1 minus cosine x divided by x is equal to 0. Therefore, this entire limit, which I boxed up in the black color, will evaluate to be nothing more but 0. And we don't even need to worry about evaluating our second limit, which I'm underlining in blue, because 0 times any limit, any value, any function will be equal to 0. So this entire thing processes down to be nothing more but 0. So we have evaluated this entire limit, which I'm circling in blue, as nothing more but 0. So all we have to do now is evaluate this limit, which I'm underlining in black. To evaluate this limit, then we evaluated and proved the derivative for the secant function. So if I scroll down and rewrite the limit that we need to process, which is the limit as h goes to 0 of sine of theta times sine of h divided by cosine of theta times cosine of h minus sine of theta times sine of h, this limit will be equal to the derivative for the secant function. So to evaluate this limit, we can apply a previous limit property of the sum of two functions, which is the limit as h goes to 0 of sine of theta, or excuse me, but this is, I think I copied it wrong. Yeah, for this one, I forgot to times it by h times cosine of theta, because we're summing these two functions, so the denominator has to remain the same. So if I rewrite this, please do excuse my previous error, we have to rewrite this because that is not equal to the derivative of a secant theta. This denominator times h times cosine of theta is equal to the derivative of the secant function. So now we can evaluate this. We can break up this limit to be equal to the limit as h goes to 0 of sine of h divided by h times the limit as h goes to 0 of sine of theta over cosine of theta times cosine of theta times cosine of h minus sine of theta times sine of h. So now we can begin to evaluate each limit piecewise, and we can apply a limit property to derive this limit, which is the limit as our input of x approaches to 0 of sine of x over x will be equal to nothing more but 1. Therefore, this limit will become 1. And all we need to do now is evaluate this limit. And to evaluate this limit, we must further break up the limit to be the product of two limits, which is now becoming 1 times the limit as h goes to 0 of sine of theta over cosine theta times the limit as h goes to 0 of 1 over cosine of theta times cosine of h minus sine of theta times sine of h. So with this, we can evaluate this limit because we know that the tangent function can be defined in terms of sine and cosine to be equal to the sine of theta over cosine of theta. Therefore, sine of theta over cosine of theta in this limit right here becomes nothing more but tangent of theta. And we can treat tangent of theta in this limit as a constant, so we can take the constant outside of this limit from the limit property of the limit as our input of x approaches to any number of n of a constant represented by c times another function represented by f of x will be equal to, if we take the constant outside of the limit, c times the limit as x goes to n of f of x. And the reason why we can treat tangent theta in this limit as a constant is because this limit has to do with regards to our change in x represented by h. As h is approaching to 0, it is not affecting the independent variable of theta. Therefore, we can treat tangent of theta as a whole as a constant. So therefore, we have taken out tangent of theta outside of this limit. So tangent of theta times the limit as h goes to 0 of 1 times this limit right here. And to evaluate that limit, we just have to substitute h is equal to 0 inside this fraction. So this becomes times 1 over cosine of theta times cosine of 0 minus sine of theta times sine of 0 radians. And to evaluate these terms, we can first evaluate the limit as h goes to 0 of 1, because we know from another limit property that the limit as our input of x approaches to any number of n of a constant represented by c will be equal to that constant. And since our constant in this limit is equal to 1, we can rewrite this entire thing to be equal to 1 times tangent of theta times 1 times, if we evaluate the denominator, cosine of 0 radians becomes 1. 1 times cosine of theta will become cosine of theta. So these two terms evaluate to be cosine of theta. And sine of 0 radians is equal to 0. And 0 times anything will be equal to 0. So this term evaluates to be 0. Cosine of theta minus 0 will be equal to cosine of theta, having a grand fraction of 1 over cosine of theta. And we know that from a trigonometric identity, which I'm going to write up here, that the secant function is equal to the 1 over cosine function. They are reciprocals of one another. So 1 over cosine theta can be rewritten as the secant of theta, hence becoming tangent of theta times secant of theta. And if we reorder this, becomes secant of theta times tangent of theta. Hence proving our derivative of the secant function to be equal to secant of theta times tangent of theta.